Swayam Prabha. Digital India. Educated India.
Namaskar. So, in last class we were discussing about the step response of RC circuit. So, we will start our discussion from that point onwards, and we will see the RC circuit response, particularly the voltage and current value, and then we will proceed for RL circuit, and we will see what would be the step response for RL circuit. So, now let us recap what we discussed in the last class. We said that when a particular time t is equal to 0, the circuit is closed, then this particular phenomena can be equivalently represented as a voltage source with one step function combined, and then the RC circuit, and we found that the equation for the RC circuit which we are seeing in the figure was derived with the help of mesh equations. Now, when we derived, we came to know that the value, that is V t at means the voltage at any particular time t, is V naught when time is less than 0. So, we assume that the capacitor is initially charged with some voltage V naught, and when the switch is closed, the response of the voltage would be for time t greater than 0 V s plus V naught minus V s into e to the power minus t by tau. So, this is what we discussed yesterday in our lecture. Now, let us see if the voltage, that is source voltage V s, is greater than initial voltage across capacitor. So, it means that V s is greater than V naught. The plot would look like as shown in the figure. So, what will happen if you see this particular equation? At time t is equal to 0, the value will start increasing. So, when we plot the curve for t less than just before 0, we will keep the value of voltage as V naught. So, what we have done, we have kept the voltage as V naught, and then after that it is V naught minus V s into power minus t by tau. So, it is now, if you keep on putting the value of various t, that is time, as 1, 2, 3, you will get the curve which would look like as shown in the figure. Now, the important thing which we have to remember is that at steady state value, that typically occurs after 5 time constants, the value of voltage across capacitor would be equal to the voltage V s, that is the source voltage. Now, let us take another condition. If capacitor is initially uncharged, that means that V naught is 0. So, what you have to do, you have to just simply put the value of V naught is equal to 0 in this case. So, what you will get is now V s into 1 minus e to the power minus t by tau for time t greater than 0. So, what will happen in that case? Your curve will start from 0. So, you will see the curve like this, where it will settle down at again at voltage V s for time t greater than 0, and for time t less than 0 it will be 0. So, in that case it will the curve will look like as shown in the figure. Finally, it will settle down to the value of V s, which is nothing but the source voltage. Now, if you are asked to find out the current through the capacitor, you have to just simply differentiate the voltage equation which we have got. So, current I at any time t will be equal to C dV by dt. Now, if you differentiate, you will get simply the value as I t is nothing but V s by R e to the power minus t by tau, and you will add u t just to make sure that you are referring to the time which is greater than 0, because this is a unit function, its value is greater than 0 when time t is greater than 0. So, this equation, which is nothing but equal to Vs upon R e to the power minus t by tau for time t greater than 0, can be equivalently represented as Vs by R e to the power minus t by tau into ut. Now, if you see these two equations, this equation is increasing exponentially, and when you see this equation, this is decreasing exponentially, which is obvious, because when the voltage settles across the capacitor equal to the source voltage, the current will eventually die out. So, what will happen, the responses, this would be the response for voltage at across capacitor. It will settle down to some value, to the value Vs at some time t that tends to infinity, and the current will start from Vs by R. So, if you put the value time t is equal to 0 here, you will get IT, that IT at time t is equal to 0, that is I naught is nothing but Vs by R, and then it is exponentially decaying. So, this will settle down after, generally it settles down after 5 time constants, because we assume that at 5 time constant the value what we get is less than 1%, means it is almost settling to a 0 value. So, that is the approximation we take, that after 5 time constants the value of either current in this case or voltage in this case will settle down to a steady state value. Now, there is an alternate method also for finding the step response of either RC or RL, because it is applicable in both of the types of circuits. What we can do, that let us see what we derived in case of voltage across capacitor, that was Vt is nothing but Vs plus V naught minus Vs into e to the power minus t by tau for any time t greater than 0. Now, if you see this particular equation, you will come to know that there are two important components in the equation. So, what you can say? You can say, let us assume that voltage V is nothing but first component Vf plus Vn, where you say that Vf is nothing but Vs and Vn is nothing but V naught minus Vs into e to the power minus t by tau. Now, what is Vn? Vn is called the natural response of the circuit, because if you remember, the sourceless RC circuit equation which we derived was similar to what is given in this equation 11, that is Vn is equal to V naught minus Vs into e to the power minus t by tau, and at that time we told that this is the response is nothing but the natural response of the circuit. So, as Vn is part of the response which decays to almost 0 after 5 time constants, it is generally termed as transient response or the natural response. Why it is called as natural response? Because it is a source free or sourceless response of the circuit, where no any external source was applied. Now, if you see Vf, Vf is known as the forced response, because it is produced by the circuit when an external force was applied. So, that means when we apply any external source like voltage source we applied in this case, or maybe the current source which you apply, so that acts as a external source for the circuit. So, what happens in that case? You term Vf is nothing but forced response. We also say this as a steady state response, because it remains for a long time period after the circuit is excited. That means, this response is the response which will be value of the either voltage at across capacitor or current through the inductor at a very large, after very large time delay. say time t tends to infinity. In that case, this would be nothing but steady state response of the circuit. So, now this steady state response is the response of the circuit at the time when time t tends to infinity. So, what you can write now, that if you see the circuit, see the equation V t is equal to V s plus V naught minus V s e to the power minus t by tau. V s, if you see the figure, the voltage across capacitor after very large time, say t tends to infinity, would be equal to V s. So, what you can say now, that the V s is the voltage at time t tends to infinity. Similarly, what is V naught? V naught is the value of voltage across capacitor at time t is equal to 0 minus, or simply you can say V 0. So, this equation which we see here can be equivalently represented as V t is nothing but V infinity plus V at 0 minus V at infinity into e to the power minus t by tau. So, this is nothing but a combination of force response and natural response of the circuit. Here V naught is the initial voltage at time t is equal to 0 plus, because what happens in case of capacitor, the voltage across capacitor cannot change instantaneously. It means that V naught at time t is equal to 0 minus and time t is equal to 0 plus will always remain same, and V infinity is nothing but the steady state or final value of the voltage across capacitor. So, now let us take one example and let us understand what we discussed till now related to RC circuit. Now, in this figure, position A is the position of the switch for a long time. Now, at time t is equal to 0, the switch is moved from A to B. So, this will become like this, and what we have to do? We have to find the value of voltage at time t for t greater than 0 and calculate the value of voltage at time t is equal to 1 second and 4 second. Now, if you see this particular circuit, the value which you need to first find out is what is the value of the voltage across capacitor at time is equal to 0 minus, means just before the switch was thrown from A to B. Now, if you see the circuit, you can easily find out what would be the value of voltage across capacitor. What would be the value? Because at time t is equal to 0, if you see the voltage source value is 24 volt. Now, we have 3 kilo ohm and 5 kilo ohm resistances. The voltage across capacitor is nothing but voltage across the 5 kilo ohm resistance. So, what we can do? We can use by simply voltage division, find out the value of voltage across capacitor, that comes out to be 15 volt. Now, since the capacitor voltage cannot change instantaneously, we can say V 0 minus is nothing but V 0 plus or V 0, that is 15 volt. So, we have found the value of V naught. Now, for time t greater than 0, switch is closed. So, what will happen in that case? If you close the switch, the equivalent circuit will look like as shown in the figure, where you have a capacitor connected and then you have the resistance and again one voltage source. The value of capacitor is 0.5 millifarad, then this value is 4 kilo ohm and voltage is plus minus, that is 30 volt. So, this would be the condition when switch is thrown from A to B. So, if you see this circuit, you will see if these are the two terminals of the circuit, the right side of that is nothing but Thevenin equivalent. which is applied across the capacitor. So, what you can say, the Thevenin equivalent for the circuit at time t greater than 0 would be looking like as shown in the figure. So, this section would be your Thevenin equivalent. So, you can simply say that RTh is nothing but 4 kilo ohm. So, what will happen in that case? Tau, that is basically the value, you can say it is RTh into C, is nothing but 4 into 10 to the power 3, because this is 10 to the power 3, that is the value of 4 kilo ohm resistance. Then what is the value of capacitor, because you need to find out the value of time constant tau, which is nothing but Thevenin resistance R into C. So, RTh you have got, value of capacitance C is 0.5 millifarad. So, that becomes 5 into 10 to the power minus 4 farad. So, when you simplify, you get the value of time constant, that is 2 seconds. Now, when you keep the circuit like this for a longer duration, the capacitor will be charged with the voltage V, which is 30 volt. So, what will happen? You can simply say that V at infinity is nothing but 30 volt. So, you got V at steady state value of voltage V is 30 volt. V0 we have calculated already, that is 15. So, you put the value of these two components and the time constant value, you will get the value of voltage at any time t is nothing but 30 plus 15 minus 30 into e to the power minus t by tau. Now, at time t is equal to 1, you put the value of t as 1, you will get the value of voltage V at t is equal to 1 is 20 volt, 20 plus 0.902 volt, and at t is equal to 4, you simplify, you will get 27.97 volt. So, we will see when time is changing from 1 to 4, the voltage across capacitor is rising, and finally, it will settle down to the steady state value, that is 30 volt. Now, let us talk about the step response for a RL circuit. Now, if you see the figure on the left, you have one R resistance and inductor, both are in series with voltage source Vs. If at time t is equal to 0, the switch is closed, means voltage is applied to the circuit, and finally, you will see that the equivalent circuit including the switching phenomena can be represented as Vs into ut, that would be the voltage source, and then R and inductor L. Suppose we need to find out the value of current I at any time t for the inductor and voltage across inductor at any time t. So, what we can do? We can use two methods to find the RL response of the circuit. First is that you can simply apply Kirchhoff's law. That means that let us say that this is the node, this is the current IR, we know that this is current IT, or you can say this is current, say IL, which is nothing but time dependent current. So, what you can say that you will simply write the equation L di by dt, that is IL plus. So, if IR plus I, you will see that IR plus IL would be equal to 0 for this when we apply KCL. So, L di by dt plus, suppose this would be the voltage V, because the voltage across inductor L is V. So, this will become V minus Vs ut divided by R equal to 0. So, this would be the simply the Kirchhoff current law application into the circuit, and you can simplify and you can find out the value of I L, which would be nothing but function of time t, or you can simply say this is I t, because the symbol I is given in the figure as current flowing through the inductor. So, this would be first case means you will apply Kirchhoff's law and solve it. But now we will use an alternate technique which we just explained, which is easier to derive and use. So, now let us say that response will be sum of natural current and force current. So, you can simply say that total current I in this particular figure is across through the inductor. So, you will say I is nothing but IF plus IN, that is force response plus natural response. Let us say that natural response is some A into e to the power minus t by tau, because you know that the natural response is always decaying, because there is no external force applied. So, whatever is there, the current which is flowing through the inductor will eventually decay out to 0. So, it will always be exponentially decaying. So, natural response we will represent it like this, and A is a constant which we have to determine, and tau is nothing but the time constant, which we know that it is L by R. Now, what would be the force response? Force response is the value of the current after a long time when switch is closed. So, when you see the circuit, the natural response essentially die outs after 5 time constant. So, what will happen at steady state condition, say time t tends to infinity, what will happen, that inductor will act as a short circuit. So, in that case the IF value, that is force response, is nothing but Vs divided by the value of resistance R. So, we have got IF is nothing but Vs by R. So, what you can write now, I is nothing but IF plus IN. So, this will become Vs by R plus A into e to the power minus t by tau. Now, next we have to find out the value of constant A. Let us assume that I naught is the initial current which is flowing through the inductor. That means at time t is equal to 0 minus, means the time just before the application of the switch, means the circuit is switched on and voltage source is applied. So, at that particular time we assume that the current flowing through inductor is I naught. So, this I naught will not come from the voltage source because it is not still applied, it will come from some other source which was initially applied and now it is continuing, and we have the value of current flowing in the inductor because of some other phenomena, and we can say that I at 0 minus is nothing but I 0 plus or equal to I naught, because we know that current flowing through the inductor cannot change instantaneously. So, because of some phenomena which was happened there in the circuit, we were having initially the current flowing I naught at time t equal to 0, and this will be maintained because the current through inductor cannot change. So, now what will happen at time t is equal to 0? If you put the value of time t equal to 0 in this will become 1, and I naught would be nothing but Vs by R plus A. So, A can be simply represented as I naught minus Vs by R. So, if you put the value of A, you will get equation as Vs by R plus I naught minus Vs by R into e to the power minus t by tau. So, if you see this particular figure and suppose Vs by R is less than I naught, so the response of the current across flowing through the inductor would be as shown in the figure. So, what we can say that the complete response of RL circuit, you can simply write that current as time t tends to infinity, that is I infinity, plus I naught minus I infinity whole into e to the power minus t by tau. I naught is the value of current at time t is equal to 0 and I infinity is the current at time t that is tends to infinity. So, these are called the initial and final values of current I. So, if you say that initially there is no current flowing through the inductor, that means I naught is equal to 0. Your current I at any time t can be represented as I is 0 when time t less than 0. For time t greater than 0, it will be Vs by R into e to the power minus t by tau. So, if you see here, since I naught is greater than Vs by R, so it is exponentially decaying, but here it will be like this when it will be settling down to Vs by R, because this is exponentially increasing value. So, we can simply say, if you apply unit step function, so we can say that I t is nothing but Vs by R into e to the power 1 minus e to the power minus t by tau into u t. So, this would be called as a step response of the RL circuit when I naught is equal to 0. So, this would be the current which would be flowing through the inductor. Now, you know that voltage V is nothing but L di by dt. So, when you differentiate the current I which we got previously, so when we differentiate, we get the value of V t is nothing but Vs into e to the power minus t by tau u t. So, now what will happen, that at time t is equal to 0, the voltage across inductor would be Vs and then it will exponentially decay to 0. So, this is just opposite to our response capacitor response, when in case of capacitor the voltage rises to its steady state value, while in case of inductor voltage settle down to 0. And similarly, current in this case is settling to a steady state value, while in case of capacitor the current will settle down to 0. So, in that way you can say that voltage current response for L and C are opposite to each other. Now, let us take one example to understand the step response of RL circuit. Let us say that we need to find out the value of I t in the figure for time t greater than 0. Now, we assume that switch has been closed for a long time and it was just opened at time t is equal to 0. So, when switch is closed for time t less than 0 and it was switched on for sufficiently long time, it means that the inductor was short circuited, and since switch was closed, so this 3 ohm resistance was also short circuited. So, what is the value of current I at time t is equal to 0? You can simply find out by applying the KVL, that is 10 volt would be applied only across through the 2 ohm resistance, and it will define the value of current in the circuit. So, I naught is nothing but 5 ampere, and now we know that the inductor current cannot change instantaneously. So, even after switching off the circuit, when we when the switch is off at time t is equal to 0, the current, that is I naught, just before the switch off of the circuit or just after of the switch off phenomena in the circuit, the current cannot change instantaneously. So, the value of current I naught will be 5 ampere. Now, when switch is off, means it is opened, the 2 ohm and 3 ohm resistances would be in series. So, what will happen in that case? The infinity at time t tends to infinity, what would be the current I infinity? If you see this figure, and if you apply voltage this for very long duration with switch is open, the inductor will again be short circuited, and then the current flowing through the inductor will be driven by the series combination of 2 ohm and 3 ohm resistances. So, in that case your I infinity would be nothing but 2 ampere. Now, if you see this particular figure, if you see the Thevenin equivalent, so what will happen, the Thevenin equivalent, it will be 10 volt plus minus in series with 5 ohm resistance. So, this would be Thevenin equivalent which you look in from the inductor side. So, RTH is nothing but 5 ohm. So, you will simply get RTH. Now, you need to find out the value of time constant tau, which will be value of L. L is given as 1 by 3, RTH is 5. So, you will get tau as 1 by 15 second. Now, you have all the values in your hand. You can simply put the values in this equation, in this expression for IT. So, this will become 2, I infinity is 2, I 0 is 5, tau is 1 by 15. So, finally, you get the value of current I flowing through the inductor is nothing but 2 plus 3 into e to the power minus 15 t ampere, and this is for time t greater than 0. So, with this we close our today's session. In this session we discussed about the step response for RC as well as RL circuit. So, in the next lecture we will continue our journey related to the step response, and we will also see the second order circuits also. Thank you.